name's Andy Crook. Today I'm looking at basic oscilloscope use. In this session we're particularly looking at time-based and triggers, and we're using a BMW X5 with an intermittent non-start problem as our donor vehicle. The vehicle's been scanned for fault codes, and the only code currently stored is a camshaft sensor problem. The vehicle is an intermittent non-start and is currently starting. So we're going to use the camshaft sensor as our signal while we look at how we adjust time bases and use triggers to steady the image on the screen. To connect to the camshaft sensor, we've got 3 pins. We've already identified using a suitable data source the ground pin, the signal pin, and the supply. So channel A, which is the blue channel, is connected to the signal. Channel B, which is the red channel, is connected to the supply, and the earth for the scope is connected to the sensor ground. What we're going to do now is start the vehicle, let the image come up on the screen, and then we're going to talk about the time base. Now we have the image on the screen. What we're going to do is pause the scope, switch off the engine to reduce the noise, and talk about the timings. Because the picoscope is a storage oscilloscope, we can see waveforms that we've already recorded just by going backwards in the waveform box. So I'm now selecting waveform 5 of 6. And on the screen, from the left to the right, is a time base of 2 seconds, represented in the time base box by 200 milliseconds per division. There are 10 divisions across the screen. Each box is represented by 200 milliseconds. So we can see the camshaft signal repeating approximately just under every 200 milliseconds. If we wanted to know exactly how often it's happening, we can use the rulers at the bottom of the screen. So ruler 1, and then ruler 2. We can see the delta, represented by the triangle, is 180.4 milliseconds, which is converted conveniently in the ruler's box to 332.6 RPM, or around about 664 engine revolutions of the crankshaft. Remembering the camshaft is at half crankshaft speed. So when we look at the image like that, it's quite easy to see what's going on. It's quite easy to see the repeating pattern of the camshaft sensor. However, if we were to reduce the time base, things change, and we'll have a look at that and how we do that when we restart the engine. Change the time base, we select the time base box, and when presented with the various options presented by the picoscope, As we've already measured how long it takes between each camshaft signal event, and it's approximately 180 milliseconds, we want a time base of 200 milliseconds across the screen, which means we have to select 20 milliseconds per division. The problem we have now is the image is moving across the screen. To prevent this, we need to use a trigger. I'll pause the scope, switch off the engine, and show you how to select a trigger. Triggers are selected using the trigger box. Once selected, get a drop-down box of the various trigger options. Starting with none, auto, repeat, and signal. The best trigger to select when you're first using an oscilloscope is auto, because it always displays something on the screen. So we will select an auto trigger. It now asks you to select what is your trigger source. So if we have a look at our image, the camshaft sensor signal is the thing that's moving across the screen, which is on channel A. So we source on channel A. The pre-trigger, which is the next box down, allows us to move the trigger point across the screen. So a 20% trigger allows the triggering point to be 20% into the screen. Because we've got 200 milliseconds across the screen, and we know it takes approximately 180 milliseconds for our event to repeat, we want to place our trigger at 10%. The next option is the trigger type. We're just using a simple edge trigger, although as you get more proficient with the oscilloscope, there are various triggering options. The threshold, the next option, is where you want the trigger to happen. Now, for the oscilloscope to use the trigger, the signal must cross the threshold. And ours, as a good example, ours is starting at just under 14 volts and dropping to 0 volts. So there's our signal. It's just under 14 volts, drops down to 0 volts. Goes back up, from 0 volts back up to just under 14 volts. So a trigger around about halfway would definitely capture the image. So we could set this at around about 7 volts. This is what we can do with the threshold box. And I've selected set. The next decision you have to make on your trigger is the direction. Do you want the trigger to happen when the voltage goes down, a falling trigger, or when the voltage goes back up from 0 to 14, which is a rising trigger? We're going to trigger on the down because that is the beginning of our event. So I'm going to select a falling trigger. Once we've done that, you can see that everything we've selected is shown in the trigger box. We'll start the scope back up. And now when we start the engine, we should see our image steady on the screen, not moving around. So unfortunately, how we've selected it means that the end of our sample isn't quite on the screen. In this case, you can grab the trigger manually and move it. Notice, we've gone down to 2%. Moving the image across that way so we can now capture the start of the next event. Selecting the correct time base for the image that you want to look at using the picoscope and then analyse is vital. Too long a time base and there's not enough detail, you end up zooming right in, looking at stuff, which isn't a bad face. It's always better to start with too large a time base with a picoscope and come in using the zoom than it is to start with too short a one and try and zoom out. When you want to look at something in detail, such as a camshaft sensor like this, selecting a trigger holds the image steady so you can analyse it. For now, if we wanted to measure the distance, once again, between these 2 points. We can do. Or we want to know how long the image, the cam sensor is held to ground. We can do. So capturing the image in a way that makes it easy to analyse is the job of the trigger. The time base allows you to select how much information you want to look at on one screen at any one time. On images or signals that repeat, having 2 on the same screen at the same time gives you a point of reference. Using the trigger allows you to do that without it dancing around the screen.
As vehicle manufacturers are installing more technology into our everyday vehicles, plus more consumers to meet the creature comforts, it's no surprise the battery technology has to change. Let's have a look at this module regarding the importance of testing the batteries to meet their ever-increasing electrical demands. After all, the battery voltage may be good, but what about the CCA?
There are various types of battery technology used on vehicles, depending on the vehicle age and technology demands. Here we have an SLI, starter, lights, ignition, or conventional wet lead-acid battery for vehicles up to 2000. The job of the battery is to start the engine and power a limited amount of consumers. Here's the AFB, Enhanced Flooded Battery. It's the entry-level start-stop battery. AFB batteries are a further development of conventional lead-acid batteries. The materials used on the surface of the positive plate guarantees that the EFB has a longer service life. EFB batteries have a low internal resistance, plus have twice the number of charging cycles in comparison with conventional SLI batteries, as well as a high load capacity. EFB batteries are suitable for the power supply of cars with entry-level start-stop systems and/or entry-level smart charging. And finally, we have the AGM, Absorbent Glass Mat. It's maintenance-free and leak-proof because the electrolyte is bound in an absorbent glass fleece. They're powerful batteries for advanced start-stop systems and have a very good cold start characteristics. An AGM battery with a warm engine can be switched off and started again several times at short intervals, without the risk or difficulties when restarting. They also provide sufficient capacity to continue to supply electrical consumers during the frequent stops and still guarantee a reliable starting. An AGM battery is the ideal energy storage unit for vehicles with advanced start-stop systems. Smart charging, STARS, which means stop-start alternator reversible systems, as well as engine recuperation, plus cars with premium equipment and sophisticated accessories. As you can see, there are various battery technologies, be sure to replace like for like. You can always upgrade, but please, please never downgrade the battery technology.
The reason why the battery technology had to change is due to the high volume of electrical demands on our everyday vehicles. Having the right battery for the right application is key and should never be compromised due to the cost of replacement. Think about how a vehicle accelerates. It steers around corners. It slows down and stops during everyday drive. For most years, the vehicle systems communicate via CAN bus. There's no physical mechanical link. All this sophisticated technology needs to be powered along with all the creature comforts, so battery reliability is key. Electric windows become slow to operate. Convertible roofs may be able to open but may not be able to close. Start-stop fails to operate, and the list just continues. These are all typical signs of a failing battery, so testing the battery at every opportunity has never been so important. Every service, any repair work, and definitely before any diagnostic work is carried out.
The IBS, Intelligent Battery Sensor, is an important part of modern day vehicles. The IBS can be found located on the negative post of the battery, not the positive post because it's on the load path of the circuit. It can then see the load drawn on the battery correctly. As consumers are active, the IBS monitors the amp drawn from the battery and will alter the charging profile or start the engine if needed. By identifying this sensor correctly connected to the battery, it is an indication that the vehicle has either smart charging or start-stop capabilities. The IBS is used to determine the battery's state of charge and state of health by measuring the battery's voltage, current and temperature of the battery. The energy demand on the battery depends on the equipment level fitted on today's cars. Systems such as ADAS, braking and fuel-saving functions such as coasting, plus energy recovery and start-stop. After all, the battery is the heart of the vehicle. The IBS sends data via a LIN bus to the vehicle's battery control module, which uses all the parameters to constantly calculate the level of charge to allow the vehicle to safely perform a stop, knowing it can start again and prevent the battery being excessively discharged. The system will also shut down systems that are classed as non-essential when needed to ensure safety systems have their allocated power when a system supply issue occurs. The IBS has a reference supply voltage to the sensor. When replacing a battery, it's vital to perform the correct procedures to ensure the battery receives the correct charging profile and ensure all electrical consumers have been correctly reset.
So now we've seen about the different vehicle technologies and components along with the battery technologies. Why should we test the battery? The battery is the heart of the car and the component that makes everything happen. Testing is essential because you can't see the battery is failing and you can't hear that the battery is failing until it's too late. The only way to find out the condition of the battery is by completing a simple battery test. A good battery should have at least 12.6 volts, but it doesn't end there. For a battery to be in good condition, you must also know if it is able to perform under heavy load, such as cranking the engine. And again, this can only be identified by testing the battery. Many of the cars coming into the second-hand market are now start-stop vehicles, and this takes a really heavy toll on the battery as it is required to power all the vehicle electrical systems when the engine is not running. There can be hundreds of control units that all require power, so having a good battery ensures that this happens. One of the main vehicle electrical systems is the power steering, and this requires huge amounts of power to assist the steering input. A customer will put their trust in you to complete a full inspection of their vehicle whenever it enters the workshop. This inspection should definitely include a battery test to make sure that the vehicle remains reliable and safe for the customer to use. After all, the tyres and antifreeze are always routinely checked without question.
During the next section, we demonstrate what appears to be a complicated task. So we've included some key points with explanations to make it easier to understand and to aid with testing batteries that you may have taken for granted or simply scroll through the next screen, which have produced inaccurate results. Whilst going through the battery tester menu, it's key to enter the correct data from the screen. This detail is very important because each quality tester has set algorithms and calculations for each battery technology, EN rating, CCAs, plus don't forget the temperature, which has a dramatic effect on the results. A good quality tester with a printout is always recommended, but it must include start-stop, EFB and AGM within its menu. So let's have a look at testing a battery.
Testing batteries is an easy process, but there may be some messages on the tester that can cause some confusion. Let's sort these out so that you can be confident in what you're doing. Not all testers will have a display like the one shown here, but the operation will be very similar on other good quality testers. Once you've identified the battery as shown previously, you can enter the information into the tester that will ensure that the result will be correct. Once connected to the battery, select what test you are doing. A battery test. This is for a standard SLI battery. A new battery test. This is a brand new battery not previously fitted to a vehicle. Or a start-stop test, an advanced battery technology test for EFB or AGM batteries. Next, where is the battery located? In vehicle or out of vehicle? Next, select the battery type. Something to note here, when a start-stop test is selected, it will only display the battery technology relevant to start-stop vehicles. Otherwise, you could select a regular flooded battery, an EFB, or an AGM flat plate. This is then followed by selecting the battery standard. This is very important, as if the wrong standard is selected, it will cause incorrect results. So there's EN, JIS, SAE, DIN and IEC. EN is the most likely option for the UK market. So then next select the battery CCA rating and input that into the tester. Now you can perform the test. You may see some of the following messages from time to time, and this is how to overcome them. Surface charge detected. This usually happens if the battery has just been recharged and not left to stand, or the car has just been driven for a distance and charged by the alternator. To remove the surface charge, turn on the headlights until the tester sees that the charge is gone. System noise detected. This is due to any electrical component using charge while the battery test is underway. But this is usually seen if there's a larger than normal consumption, such as a fuel lift pump or an injection solenoid, or it can be a faulty component such as a bonnet pin switch. Next, battery temperature. The battery temperature is very important, as hotter or colder conditions can cause an increase or decrease to the internal resistance of the battery, and it can give an inaccurate reading if it is not known by the tester. The other likely messages are pretty self-explanatory. So for example, reverse connection or check connection. When the test is complete, even though the tester will likely give you an accurate response, it is helpful to understand why it is given that response. The voltage reading shows battery charge available. A little understood but very important factor is the CCA rating. This shows how much power the battery has to crank the engine. If this is lower than the rating of the battery, it indicates there could be a problem with the power of the battery. This battery is rated at 680 CCA, but the measured value is much lower at 342. This, also coupled with the low battery voltage of just 12.4 volts, indicates that the battery is unable to provide continued power to crank the engine and supply power when the engine is stopped. This means that the battery needs replacing. Understanding this will help you to understand the condition of the battery if you ever use a tester that doesn't provide a result other than the figures measured. However, a good quality tester will always show you a worded result as well as the figures measured. So from everything that you've seen in this video, we hope that you will now have a better understanding of battery and vehicle technology advancements and the importance of testing batteries. Thanks for watching from the UK Varta team.
Remember, it all starts with Varta.
Hi, I'm Peter Melville from HEVRA, and we're going to have a look at some cooling systems. So we've got two vehicles here. Both of them have one liquid cooling system and one refrigerant cooling system, but they're very different in the way they work. So we can talk about those. So first up we have this Tesla Model S, and we've taken a few bits off this car so that we can see some of the parts we're going to talk about. And on the screen here I have a diagram of how the various cooling systems work and how they integrate with each other. So we'll talk about the refrigerant system first of all, which is this brightly coloured one. Now the thing you need to know for the purposes of this is that where we increase the pressure is where we increase the temperature, and where we reduce the pressure is where we reduce the temperature, and that's the same for all refrigerant systems. Now we choose a refrigerant because it can actually change state, which means it can absorb a lot more energy than if we were just pumping a gas round and changing its temperature. But that's the basic principle. So increase the pressure and it increases the temperature, which is why your compressor in the workshop is hot. And when we reduce the pressure, that's where we reduce the temperature, which is why your air tools and aerosols are normally cold because the pressure's reducing. And the basic principle of air conditioning is that we can increase the pressure and therefore the temperature on this side. We can take the temperature out of it with the condenser, and then when we reduce the pressure again, we can end up with it colder than it was before, and that's the basic principle. So that's common for all air conditioning systems. So what's different about this? So on the face of it, not a huge amount. So we start off with the compressor. The refrigerant flow is in this direction, so it comes out of the compressor and then it goes straight into the condenser. So similar to a turbo going into cooler, we create the pressure and then we get rid of the heat. So we've got compressor, condenser. Now on this model we do actually have two condensers. So our first one is on this side and our second one is here on this side. But in terms of the concept of how it works, it's the same as having one. It's purely for packaging reasons that we've got one on either side of the car like that. We then have our receiver dryer, which is an accumulator that's not relevant to the actual cooling process. But when we get to here, we now split this refrigerant system into two parts. And we have little electronic valves on both of those that can change the flow of the refrigerant. So what we can do is, this is our normal evaporator that's inside the car, same as any other car. So we can open this valve and we can close this valve and we can circulate the refrigerant around here, and it's exactly the same as the air conditioning system in any other car. What we can also do is we can open this valve and we can also cool down this heat exchanger. So we'll talk about that a bit more in a moment, but we can run the compressor and we can either cool the interior of the car or the heat exchanger, or both, depending on what the cooling needs are. So if we look at the liquid cooling system, which we've got shown in green, what we have here is we have approximately 1.5 different cooling systems. And the reason I say 1.5 is because under normal operation we have one cooling system. So our coolant flows in this direction, so this is our radiator on the front of the car, which is much the same as a radiator in any other car. And the coolant flows along here, it goes through this valve. These round things are water pumps, and it goes through our heat exchanger, and then it goes through this little heating unit. I'll talk a little bit more about these in a moment. It goes through the battery pack, and in parallel through our DC-DC converter, and then it comes round here through another pump, through our onboard chargers, and our drive units, which are our motors and inverters for driving the vehicle, and then back to the radiator. So it circulates around like so. Now that works very well. It keeps everything, stops everything from getting too hot, but there are some flaws with this system which we can improve on. So there's one situation where we might want to cool the drive units and at the same time heat the battery pack. And that seems very wasteful. If we turn this heater on, we're then going to be heating up this part of the circuit, and we're then inadvertently going to be heating up our electronics, which we don't want to do. So the battery pack is a bit like a combustion engine in that we have an ideal temperature window that we want it to operate in, but the electronics, they just like to be not too hot. So we have different cooling needs, and this is why we make the system a little bit more complicated. So let's say we're driving on an extremely cold day, but we're driving the car moderately hard. We will then be creating waste heat in our drive unit from driving the vehicle, but actually our battery is still below its optimum working temperature. And what it's then desirable to do, it's then desirable to make the best use of the available energy to actually move the heat from the drive unit into the battery pack, and then we don't have to use our heater. So the way we do this is we have a little valve here, which is our radiator bypass valve, which is located down here. And that then allows the coolant to circulate the system without going through the radiator. So that means that although we're moving heat around the system, we're not actually getting rid of any heat. And instead, what we can do is we can then put our heat through our battery pack. So what we're now doing is cooling our drive units and using the heat to warm the battery pack. And if that heat isn't enough, we can turn this heater on, but the warm coolant that's flowing out of our drive units and into this system, we can then measure the temperature of that, and if necessary, we can turn the battery pack cooling heater on as well. Okay, so there's another circumstance as well where we might want to change this, and that is under very hot conditions. So what we find is we've got our cooling system, and now that stops all the electronics getting hot, and that works really well. But if you imagine you're driving in a very hot climate and you're really hammering the car and everything's getting quite hot, even if the battery cooling system is 100% efficient, the coldest temperature we can possibly get that battery to is the same as the ambient temperature, because we're taking the heat out of the battery pack and then we're dumping it in the radiator. We can have the radiator fans going full blast and everything, but the coldest we can possibly get that to is the same as the ambient temperature. And in, not so much here in the UK, but in some markets in the world, you know, the ambient temperature might be 40 or nearly 50 degrees, which is actually above our optimum battery pack temperature. So what we can then do is we can then use this four-way valve, which is this part here, to split this into two cooling systems, which is why I said the car's got 1.5 cooling systems. So what we then do is our drive units are then cooled in much the same way as before. So our coolant circulates along here. We will open this valve to make use of the radiator, and our valve will then link this pipe to this pipe. So we then have a coolant loop that looks like this, and this is why we need to have coolant pumps in both halves of the circuit. And what we can then do is then circulate the battery coolant around this circuit. Now obviously we don't have a radiator in that circuit, but what we can do is we can use our heat exchanger with the refrigerant system, and that is able to reduce that coolant temperature to less than the ambient temperature. So in order to get the best possible performance out of the battery pack, we can use this to cool the battery to as cold as we possibly want it, and we will just circulate coolant around this smaller loop. So we've then got two completely separate cooling loops. Okay. Also shown on this diagram, we have a bypass for the heat exchanger so that coolant can avoid flowing through the heat exchanger, although they later decided on later cars like this, they've done away with that because all they need to do is close the refrigerant flow and the coolant can just flow through it. So later cars like this, they've actually done away with that little branch of the circuit. So that's how they can use one relatively simple cooling circuit to cool the onboard electronics, warm the battery, and also cool the battery to colder than the atmospheric temperature if required. And just to show you some of the components, this is our heat exchanger. So you'll see we've got a coolant pipe coming in, so this pump is pumping in this direction. So you'll see coolant coming into here. This little valve allows us to control the refrigerant flowing through it, so we can close it off if we want cabin cooling but not battery cooling. And then this joins up with the rest of the coolant circuit. You can see the second pump in that area, and we can see our third coolant pump in this area here. So now moving on to the leaf. So on this vehicle we still have one header tank for the coolant, and we still have one refrigerant system, but the cooling of this car is very different to what we've seen on the Tesla Model S. So if I show you the diagram first of all, the cooling system on this car is very basic. So we just have a coolant that flows through the charger, through the inverter and through the motor, and then through the radiator, and the pump runs at the required speed to keep all those at the optimum temperatures. Now on the Leaf we don't have a battery cooling or heating system at all. What we do is the battery is capable at operating under the temperatures that it sees in normal life. It won't necessarily get the absolute optimum performance under all conditions as you would have seen with the Tesla, but it suits the nature of the car and it makes the car a lot simpler to build. Now the interesting part of the Leaf, which is actually more sophisticated than the Tesla, is on the cabin heating. So what we have on the cabin heating, the Leaf, is we have something called an air source heat pump, which you may have heard of in buildings, but it's a fairly new thing for vehicles. So this is integrated within the existing refrigerant system. So if we look at how the cooling part of it works, first of all, we have our compressor, and you'll see we've got an extra couple of valves, and I'll talk about these in a moment. But first of all, the refrigerant leaves our compressor, so it's in a high pressure, high temperature state, and it then goes into a condenser that's in the inside of the car. Now, that will obviously cause that to be at a high temperature, but what we do is we arrange our heater flaps so that the air coming into the car isn't going through that when we want the car to cool inside. So you'll also see that we've got a restriction in this part of the circuit, and with this valve open, this effectively is doing nothing. Effectively, this entire part of the circuit is just acting as pipe work. So there's no airflow through this, so we don't get any cooling here. There's no pressure change across here, so we don't get any temperature change across here. But what we do get is, by the way it finds itself to the front of the vehicle, we then have our condenser on the front of the vehicle, same as any other car, and that is where it gives up its heat. And it then comes along, it goes through a three-way valve, and it then finds its way through another restriction into the evaporator inside the vehicle. Now, because we have that restriction there, that's where we lose the pressure, we therefore lose the temperature, and that cools the inside of the vehicle, same as any other car. So if you just think of this part of the system as pipe work, it is effectively exactly the same as the air conditioning system in any other car. If we then look at the system when it's in heating mode, what we do is, first of all, we close this valve, and then we change the direction of this valve. So what we now have, we also move the flaps inside the heater box as well, so we're now changing our flow of the air through the heater box, which isn't shown in this diagram. So what we now do is we now pump our hot, high pressure refrigerant out of our compressor as before. It goes into the condenser inside the car, but because we've now got a restriction here, this means that we've got an increase in pressure in all of this part of the circuit, because we're pushing pressure out of here and it can't get through this restriction. So all of this part of the circuit is now in high pressure, so that means it's actually got a very high temperature in order to warm the cabin. It then leaves this part of the circuit very cold, where it finds its way back to the front of the car, and because it's now very cold, it can now absorb heat from the ambient air, a bit like we would normally pick up heat from inside the car. We're now effectively air conditioning the air outside the car, collecting this heat, and it's now not going to bother going through the interior evaporator and this other restriction. It's going to go on a little shortcut and find its way back to the compressor, where it's already had an increase in temperature here, and a further increase in pressure and temperature through the compressor means that we can drop all of our heat inside the vehicle. So I'll show you the components on the Leaf. So as I say, the cooling system is very basic on here. We've got our header tank, we've got our water pump, and the cooling just flows through all of the components and the radiator, and the pump just runs at the speed required for cooling. And then this is where we have our refrigerant valves. So you can see here is our three-way valve, here is our two-way valve, and these valves will change when the requirements change for cooling or heating the cabin. So if we get a problem with this, we can potentially end up, when we've got the heater on, we can end up accidentally cooling the cabin, or when we've got the air conditioning on, we can end up accidentally heating the cabin if we've got a problem with one of those valves. So the way we check those valves is by using something like an infrared thermometer or a thermal imaging camera. We can see where the hot parts of the circuit are, where the cool parts of the circuit are, and referring to the diagram, we can see if those valves are in the correct position. If we then suspect a fault with the valve, we can then look at the electrical control of the valve and see whether it's receiving the right signal to get it to the right position, so whether it's a fault with the valve or whether it's a fault with the electrical supply to it. So the one thing that is quite important with a lot of these systems is because we've got these valves in the refrigerant circuit and the valves potentially in the liquid cooling circuit as well, we do need to make sure we follow the right procedures to fill and drain the circuit, because potentially you're only draining a small part of the circuit, and even with an air conditioning regas, you're potentially only regassing a small part of the circuit unless you've got the valves open. So it's important to refer to the manufacturer for this information. You can ask us if you're one of our members, or you can refer directly to the manufacturer to find out what the correct procedure is to regas that vehicle, because on some vehicles, such as this one, those valves are all open by default and you can access the entire circuit, and some other vehicles, such as this one, the valves are actually closed by default, and if you try and do an air conditioning regas, you'll find that you need to then connect diagnostic equipment, tell the vehicle that you're doing a regas. All the valves will then be put to the optimum position to let the whole system be joined together so that you can do the regas. And if it's got a complex coolant circuit like this, you put it into bleeding mode, and again it will put all the valves in a suitable position, especially when you only have one header tank like this, in order to fill the whole circuit. It will run the pumps as well in order to circulate the coolant, in order to make sure those cooling systems are properly bled.